Hello, and welcome back to another session of RISC-V emulation in a high-level language. And last time I left off, we had been able to write Hello World on the screen, which is a big step, but now we're going to take a little step backwards and look at the final class of instructions that we haven't implemented yet in our emulator. And in order to put a basis for the discussion, we're going to go to the manual and take a look at the instruction classes that we've seen so far in the emulator, and we will then implementing the one final missing class. So this is the RISC-V instruction manual, and as you can see here, there are several different types of instruction formats defined by the manual. And we've implemented all of them except one. We've implemented the R type in instructions like add and multiply. We've implemented the I type in the very popular add I instruction, and also in the load instructions that load register values out of memory. We also implemented the store instructions so that we can store data into memory. We implemented the B type instructions so that we could perform conditional branches depending on the result of a comparison. And then we also implemented the J type instructions, which allowed us to jump around in the outer space. The final one, U type, becomes useful for two scenarios. One of them is the handling of large numbers, and the other one is in the implementation of PC relative addressing, and we'll touch upon that once we're finished the discussion of large numbers. So what do I mean by large numbers? Well, if we look at the add I instruction that we've been using for most of this series, the add I instruction takes the two operands that are register. So I could say R1, R2, and then there's a number, an immediate value, something like this. And what the assembler will do is it will take these field identifiers. R1 would become a 1 that gets stored in this field of the instruction. The R2 would get stored in this field. And then the 3, 2, 4 that we see here would be stored in the 12 bits that are reserved for the immediate value of the I-type instruction. The problem occurs when the number that you want to store is larger than 12 bits. What are you going to do then? Because it will not fit here. And so to solve the problem, we introduce a second instruction that is called LUI for load upper immediate. And the format is, it only takes two arguments, R1, which is the destination register, and then the immediate value, which is some numerical value like this, which is treated as an immediate value. But what happens is when you execute the LUI instruction, this immediate value that we see here is actually shifted over by 12 bits. So recall that these 20 bits don't fill up a full 32-bit word. There are still 12 bits remaining, and those 12 bits will be filled with zeros. So in order to create a large number, suppose that I wanted to generate the very large number in hexadecimal 1, 2, 3, 4, 5, 6, 7, 8. Now that is a 32-bit number. It fills up every single bit of the 32-bit word. So how would I go about doing this? Well, what I'd need to do is rip it apart into two halves. The bottom 12 bits is 3 hexadecimal digits, 6, 7, 8. Those would have to be loaded with an add I instruction, and then the upper bits 1, 2, 3, 4, 5 would be loaded with a load upper I immediate instruction. So we would write something like this: load UI, and then R1, and then 0, 1, 2, 3, 4, 5, and then add I, R1, R1, 0, 6, 7, 8. So the assumption is that after these two instructions are executed, R1 will have 1, 2, 3, 4, 5, 6, 7, 8. So what we'll do is we'll write our emulator to do exactly this. The first thing, though, is we have to implement the assembly language or the assembler part, so that we can actually create instructions of this type LUI. So what we'll do is we'll go over to the assembler tests, and we will add a new test for LUI. And what we'll do is we'll grab the opcode straight from the cookbook, the manual. This is the specification that we have to follow, and this is the instruction. Oh, here we go. Nice. So we'll run the test. We'll have this, and then the actual bit pattern that we want to do is going to be 5. Well, let's do 1, 2, 3, 4, 5. So this would be 1, 2, 3, 4, 5. That's 20 bits. And then the register that we're going to be putting it into is R1. And then the opcode is this little piece right here. Okay, so there's our word, and then the assembler instruction is going to be ASM mnemonics LUI, and then we're going to pass in the destination register 1, and then the numeric constant 1, 2, 3, 4, 5, like that. Now we haven't implemented this enum member yet, so let's implement that. And now, if we run the unit tests, we expect to get a failure because we have not actually implemented the assembly language for this. Oh, wait a minute, there's a problem. Oh, I thought I added it, but all right. There it is. I'm not sure why we're having a problem here, but let's just build everything from scratch. All right, let's try this again. Right. The ASM function requires 4 arguments. So this instruction only takes 2 operands, so there's a dummy third argument or third parameter that we're just going to ignore this 0, basically. So we will refactor the ASM function in the future, I promise. All right, so for now, we'll live with that, and we'll put that 0 at the end there. Okay, this is what I was expecting, that we haven't implemented an assembler for LUI. So let's go ahead and do that. So we'll need to create a new function called ASMU, which takes the mnemonic, which again is this piece. And then there is no funct7 and funct3. There is just a destination register and a source register. Notice how we are ignoring src2. Great, so let's implement ASMU. So ASMU will be very similar to ASMI, except that it only takes 1 argument, not 2, and it doesn't take a funct3. And then what we'll do is we can scratch this, get rid of that, this, and then we take the number that we're passed in, and we're going to shift it to the right by 7 plus 2, 12 bits. 12 bits. And any bits that are higher than this will get thrown out. So that's source 1 shifted right by 12 bits. Okay. And this is ASMU. Now let's run our unit tests, and hopefully everything is hunky-dory. Looks good. So now to the emulator part. We need to write an emulator for this. So we will do a similar test. And here what we'll do is we'll combine the effect of an LUI and an add-I to give us that result that I showed on screen earlier. So we run test, and the instructions are ASM, first on LUI, and we pass it register 1 to write the result to, and then 5, 6, 7, 8, 4, 5, 6, 7, 8. No, sorry. 1, 2, 3, 4, 5, of course. So those are the high parts. And then the extra 0, which we'll ignore. And then we ASM an add-I into R1, take the existing value in R1, and then add on the last 12 bits, which are going to be 6, 7, 8. So if everything is working well, then at the end of all this, we will have this reconstituted constant 1, 2, 3, 4, 5, 6, 7, 8 hexadecimal inside register 1. Let's run our unit test. And it fails because we haven't implemented this major opcode. So let's grab the major opcode for LUI and find a place where it should go. Now about here. So there it is, and this is LUI that we're implementing. So we need the destination register and the IM1 immediate value. So let's introduce a variable called uIm for unsigned immediate value, and then we need a bit field for this. So let's create one. The bit field starts at position 12 and is 20 bits wide. So let's take this one and adapt it. 20 bits wide, 20 bits wide. Nice. Now we go back to our what was it? JAL. Where did I put LUI? There it is. Okay. So what we need to do is extract destination, which is going to be in the destination bit field. And then we need the unsigned immediate value, which is bit field 12, length 20, and extract that. And then what we do is we want to write to the destination register the value which is obtained by taking the immediate value that we extracted out of the register and shifting it to the right by 12. So we will say that will do the trick. And let's make that an unsigned value, please. Okay. What's the problem now? There we go. All right, let's run our unit tests to verify that this indeed is operating as expected. And we have a green bar, which means that everything is working great. So now we can write in our assembly language program two instruction sequences like this, where you first specify the higher part of the number that you want to use, put that into register 1. The lower 12 bits are going to be filled with zeros, and then we add these remaining bits to that upper half. Okay, so now that we are done with this part, we're going to take a look at another instruction, which also is of type U, which is AIUPC. And in order to discussion about that, we'll go back to our little sample piece of code here. So suppose that for some reason I need to get the address of this instruction in stir1. It so happens that my instruction is located at address 10000, etc. hexadecimal. But I'm not guaranteed this. In a dynamic link library, my library could be loaded at any arbitrary memory address in memory. So I cannot make the assumption that the data is always at this particular address. But I can make the assumption that the data is located before me at some well-known fixed distance from wherever my code is executing. We're going to use this new instruction called AIUPC, which means add upper immediate to the program counter. What does that mean? Well, recall that we have this program counter notion. The processor has to keep track of where exactly the next instruction that it executes is going to be fetched from in memory. Now, if I were to execute this instruction at address 1000004, then right before this gets executed, the program counter has exactly this value. So what this would do, this instruction here would do, is it would take the existing value of the program counter, which is this number ending in 4, and then it would add the second operand shifted right by 12 bits, and we'll get into why that is in a bit. Now, the sum of the program counter and these upper bits then gets stored into R1. Since I'm using 0, 0 gets added to the program counter. So at the end of this instruction, the R1 register will contain the value 1000004. Now then what I could do is take that value of R1 and then subtract 4 from it. That is by adding -4 to it. And what I would then have in R1 is exactly the address of instr1. And then what I could do is I could use the load word instruction to read whatever R1 is pointing to, which is this instruction, and then load that into register 2. Now, if the dynamic link loader moves my code so that it suddenly isn't at this address, my code does not have to change because it's always referring to the instruction 1 by a program counter relative or PC relative reference of -4. So what we're going to do now is we're going to implement AIUPC to make this to implement this. So it's the same dance as before. We go to the assembler tests and we add a new test case. And in this case, it's AIUPC, and the opcode is different. It's this value now. And it's also going to change over here, but we'll leave everything else the same. It's the same instruction format. We'll also add this new enum member. Let's make sure we save. Let's go there to make sure it's there. It's there. Great. And now if I try to run this, these unit tests, we'll get a failure because we haven't implemented the assembler for AIUPC, which was expected. So now we find LUI, and we'll just implement it the same way as LUI AIUPC, but the opcode is different. It's that code. And now if I run my unit tests, I expect to get the correctly assembled word. Unit tests are passing. So now we need to go to the emulator half and do the same thing. Here we're going to test that we have a working emulation of AIUPC. And to do that, we change our code to this. And so when we start our unit test, PC is 0. AIUPC will be added. We'll be adding 1, 2, 3, 4, 5 plus 3 extra digits of 0 to PC. That will give us 0, 1, 2, 3, 4, 5, and then 3 zeros. That gets stored in register 1. And then after that, we're going to add 5, 6, 7, 8 to it. End result is this mess down here. What we could do, of course, is change the instruction pointer, but let's not worry about that for now. Let's trust in ourselves that we get this written correctly. So this should work the same way as before, but of course we haven't implemented AIUPC yet, so we'll get a failure. All right, so now we need to implement that. And what was the major opcode? It was this. Let's find. After this block, maybe? Yep, this would be a good. I want to put the cases in numerical order. This is then AUIPC, and just like, let's find LUI because it does pretty much the same thing, except instead of writing this value immediately, we want to add it to the instruction pointer, our program counter. So we take the program counter, we take the immediate value, shift it to the right by 12, add it to the counter, and then we store that into the destination register. So if we run this, all of our unit tests pass. So that's great news. Why don't we commit the work that we have so far? I don't want to lose any work. So let's see what we have. We have a few changes. So LUI and a UIPC. All right. So we have now implemented at least one instruction of each of the RISC-V instruction format types. The remaining instructions, which are detailed in this document here, are going to be more of the same. And I'm not going to bother viewers watching me do this because it's going to be quite repetitive for no additional learnings. So what I'll do before next time is I'll implement the remaining instructions in order to prepare ourselves for our next step in learning RISC-V assembly. Because now that we have, well, once I finished implementing those functions, we will have a fully functional emulator, and so now we could, in theory, do whatever we want. And what I would like to do is start implementing more complex programs using RISC-V assembler and introducing some notions about assembly language programming. I'm also going to implement a new version of the assembler, because right now when we write assembly language programs, we have to write them using this awkward style where we call this function asm all the time. And there are better ways to do this. In particular, what we would like to do is be able to give the assembler that we will be working on an assembly language file, a text file that contains assembly language. And then what we can do is just immediately convert that into RISC-V machine language. We're going to be writing a text assembler. So until next time, I wish you all happy hacking.